Hello. In this lesson, I want to go over some calculator techniques for AP Calculus. So I've got a few example problems for us to work. The first thing I want to do is solve 0 equals 0.9x squared minus 3x plus 6x cubed minus 5. So the TI-89 actually has some solver features to it. So we can select from the Algebra 2 menu, we can select from the Algebra F2 menu, sorry. So we can type in the equation. The equation was, let me pull that over right quick. I'm going to make it small so we can kind of hopefully see both. Let's see, I should be able to minimize this ribbon, right? Well, that's okay. Well, here's the equation. And let me adjust this right quick. All right. Okay, so I'm going to type in 0.9x caret 2 minus 3x plus 6x cubed minus 5 equals 0. And then you say comma x for what you're solving for. So this is something that TA89 should be able to do. And I'm in a habit of always getting approximate solutions. You could set your mode to not be auto, and you'll see it gives me one answer. Well, this is because this is a polynomial, and there are well-known techniques for approximating solutions of polynomials. Newton's method, which uses differentials, is often taught in calculus. There's Euler's methods. There's just really well-known ways for it to do this. This polynomial could not be solved algebraically. It doesn't have a rational root. You would have to use some sort of approximation techniques. Well, the AP Calculus test writers, in their infinite wisdom and great talent, are very good at making equations that break a TI-89 or any other algebraic solver. And the TI-89, instead of simply letting you break, sometimes, usually that's by pressing the on button, kind of a flaw in its design is it actually gets caught in a loop and it won't stop at all. You got to take out not the batteries, you got to take out the memory battery, the little watch battery. So we really want to avoid doing this, especially if it's got a mix of trig and exponentials in it. They just are trig and polynomials. This is not a good idea. So let's look at a different way to solve this. We're going to go to Diamond F1. And we're going to go ahead and type in the equation here, 0.9x squared. Remember, our whole purpose is to solve for when this equals 0. Okay, now I want to start with my zoom being standard, zoom standard, so I'll hit the 6 there. And this is where I want to see, right here. Now, if you, for some reason, can't see the graph very well, and that happens sometimes because it's really small and it hugs the x-axis, or it's off on the side, you need to have a way to figure out some things. Trace is a decent function to use. You can start tracing the function. Let's see here, F2 is zoom. They do have some different things you can do. Zoom standard, of course, we've seen. Zoom fit will sometimes help you. It'll try and fit the window for the graph. So that's available. But really nothing's better than just going to your table or looking at the problem and seeing, once you get to your table, diamond table, you could start seeing some raw data and seeing like, oh, okay, I'm up here in the hundreds, or, you have to look at a lot of times the information in the problem, like say it's defined from 0 to 5, will tell you to limit your x's from there. But one thing that's nice is we're not necessarily looking to see any perfect picture. I just want to see this right here where it crosses the x-axis. So what I'm going to do is I'm going to find that 0. You might prefer to zoom box it. Once you zoom box, you just use your arrow keys to position this in a place where you can get right around the 0 that you're looking for. And there we go. We'll press enter. And you can see that it kind of goes right through there. And I'm going to go F5, go to math, and I'm going to select 2 for 0. And it says lower bound, and it doesn't, in this case, it is actually below the 0, but that's not what it means. What it means is it wants the lower bound of the x interval that it's going to start searching. It's simply going to evaluate like every pixel at a small interval and see the y value that gets closest to 0. If it gets one that underflows the calculator, which means it's so close to 0 that it just responds 0, perfect. If not, sometimes you'll get a value like, scientific notation, engineering exponent -11, or, which means like there's 10 decimal point, then 10 zeros before the number. So it's going to find in that interval at the predefined step size, and you can actually adjust that, make it more accurate, but it'll be slower. It will find the value closest to 0 on that interval. Okay. And you want to click on there, and you'll notice, it makes an arrow pointing to the right, and then I'll come up here. And you want to make sure that the y-coordinate here is changing signs. If you don't, you usually get an error called no sign change. It means you gave me a bound in which there was no change in the y-coordinate signs. All right, and there it goes. So you can see this one did not give me exactly 0, but that's number basically 0. 1.053 is what we're going to say is the answer, which is remarkably different than this one. Why is that? Probably because I didn't type it in correctly. Let me see. 0.9 x squared minus 3x plus 6x cubed minus 5. And what did I do on the y equals? 0.9 x squared minus, oops. Okay, well, that was fantastic. Human error, right? Doesn't know how to interpret what I mean, unfortunately. It can only interpret what I do. So same process, F5, we're going to find a 0. And we'll go from there to there. And there it is. Okay, 1.068, that's a little bit better. All right, next problem I want to look at is, what if you had to find the derivative of a function? So on the AP exam, if you are just asked to find, like, say, what's the velocity at t equals 4 and you have position, well, you can just evaluate a numeric derivative. But if you have to find and use, if you have to find and use a derivative to solve something, like say I have to find when velocity is equal to 0, then I'm finding the derivative and then solving it. You really need to show what the derivative is. Don't have to show work about how you got it. You can assume you just took the derivative in one step. Now, this calculator will always be able to take a derivative, so let's take a look at how to do that. You can find it from the F3 menu. Not sure why this gets stuck sometimes, but this is not the perfect emulator, but anyway, that's the calculus menu. There it is. You can go there and select the differentiate, or you can just hit second 8, which brings that up immediately. You have the second 8's got the D for differentiate. And let's type in our derivative. We're going to do second cosine x squared minus 3x times the natural log of x. So natural log is right here. Really important that you do not say x natural log x. That would be a huge problem. If you do that, what it's going to think is that you mean some variable called xln. Okay? Not good. It's got to have times. Don't have two letters next to each other unless they go together. All right, next we need to tell it with respect to what? What are you taking the derivative with respect to? We're taking it with respect to x in this case. Close the parentheses, and it gives me a derivative. Make sure you check your pretty print. You'll see they put a time sign between the 3 and the x. It's, they don't use any implied multiply. And that looks good. So we can just write that down and then use it as such. Now, if you're given just a derivative, a function, and it just needs a derivative of a specific value, then you should be taking the derivative like this. You should be telling it numerically what to do. So I'll do, let's see here, where's it? E to the negative, we're doing 4x cubed minus e to the 0.4 times cosine x. All that's in the exponential, minus 9x times the square root of x, comma, with respect to x. If you want the second derivative, you do comma 2. That's the second derivative. We're not going to do that. Then close parentheses, then hit the such that key, x equals 3. And that will find our derivative and evaluate it at that number. Okay, let's take a look at one more application problem. Suppose we have the position of a particle is traveling on the, let me readjust this here so we can see both of these. Now it's going to get a little small on me, I know. See if I can't hide this ribbon. There we go, that'll make it better. Okay, so we're going to find the position of the particle when it changes from moving left to right. So what we're going to do is first we're going to find the derivative. So I'm going to find the derivative of this function. 0.5 t, oh, I need to take the opposite, 0.5 t cubed minus 3 times the cosine of, actually, you know what, I'm not going to use t, I'm going to go ahead and use x because I'm going to show you something I can do with that. So I got minus 3 cosine e to the negative square root of x minus 3x comma x. So there's our derivative, which we could have done by hand. Oh, too many arguments. What do I got here? Must have a comma somewhere. Or closed off my parenthesis on accident. There. Okay, we got that closes that parenthesis. That closes that one. Oh, looks like I'm missing one more. Okay, so that looks good. Make sure you check your pretty print up here, that it looks exactly like what it does on your paper, and then that's our derivative, okay? But if you arrow up, watch what I can do. I can say diamond, and then I can hit this up arrow, and it's copy. Isn't that pretty neat? I got copy. Now when I go to, let me just escape from here, and I'll go to the y equals. Yeah, it's doing that thing where it won't let me. Maybe it will now. No. Ah, there it is. Okay. I can actually say diamond paste. And there it is. There's my derivative right there where I need it. We're going to graph this now. Okay. And I don't think that stop. I got like a perfect zoom, but I want to. All right, fine. We'll let it finish. But this is actually a perfect zoom. But let's pretend that we weren't so lucky. And let's go back to zoom standard and see what we have. We're looking for the position of the particle when it changes from moving left to right. Well, we're going to change from moving left to right when our velocity function moves from negative to positive. And the graph is so nice because we can see that. We can see the changing from negative to positive. We don't have to test regions or anything like that. So let's just get that 0 right there. Perfect. 0, and I will start over here. And I'll go to over here. And I get 1.440. So that's a good value right there. And I believe that if I do that, I think I might be able to say x and never mind. There used to be a way you could do that. You could like make it appear. Oops, wrong menu. All right, diamond, graph. There it is. All right, let's find that 0 one more time. Lower bound, upper bound, and it's 1.440. So help me remember that, 1.440. I'll write it down on a little scratch paper here. All right, now that I got that, let's evaluate our position function at that moment. So I typed in that position function here, right? So I'll just get rid of this derivative portion. By the way, second left arrow takes you all the way to the top front of a line. That's kind of handy to know. Okay, and second that arrow to go all the way back to the end. And we'll say such that, we were using x here, x equals 1.440. So that's the time when it changes direction from left to right, and that's its position, negative 5.692. All right, well, I hope you found this little review of the graphing calculator helpful. Take care.